had started last time, which were the symmetry identities. And let's just recall them real quick. So, if you add a multiple of 2 pi to an angle, you don't change the trig functions. And if you like, that was just because 2 pi k is a bunch of full evolutions. Those don't affect any of the trig functions. The next thing we did is we talked about, well, let's actually open up to the relevant page. Next thing we did is we thought about what cosine of minus theta is. And it's the same thing as 2 pi minus theta, and there's a reason I have that 2 pi minus in addition to there. So we found that negates sine and preserves cosine. And the reason for that is, thinking about what that does to the angle, you're exactly reflecting over the y-axis, over the x-axis. Was pi minus theta next or pi plus theta? Pi minus theta. So, I know it's like projected right there, but let's think about what pi minus theta does to an angle. Because that, I think, is more relevant than just remembering the entries in this table. If you want to think about what pi minus an angle is, let's like hand wave the picture. So on the one hand, you can rotate up by theta. On the other hand, you can rotate around by pi, so half of a revolution, and then back by theta. How do those two angles compare?
They're flipped over the y-axis.
Flipped over the y-axis. So how should their sine values compare?
The x values are going to be negative, the y is going to be the same.
X values are negative each other, so the y's are the same. So the sines stay the same, because sine is the y coordinate. And maybe instead of like saying the rest of them that way, let's think about what symmetries these just what symmetries these correspond to. Let's write it right on the paper. So when you make an angle negative, you reflect over x-axis. When you do pi minus theta, you reflect over y-axis. What about when you do pi plus theta? What symmetry does that?
Just be over the x-axis, going clockwise, so be well, maybe not, I'm not sure.
Not quite that. Let's maybe even, here's a handy picture. So rotating by an angle theta would be maybe doing that. Pi radians is another half of a full revolution. So let's take this and now add half of a revolution to it. Points in that direction now. What symmetry is that? Reflection over the origin. And let's see if that holds up. X value becomes negative, Y value becomes negative. Seem believable? And we did this last one, I'm going to give myself space, by thinking about right triangles. Pi and pi over 2, theta and pi over 2 minus theta, those are two opposite angles you would see in a right triangle. So you can use SOHCAHTOA to say, well, cosine is adjacent over hypotenuse. That'll be opposite over hypotenuse for the opposite angle. So sine and cosine will swap. On the other hand, let's just maybe even see those values and think about what that means. So the x value, the cosine, becomes the y value, and the y value becomes the x value. Is that like a symmetry that we've seen in the past? X's and y values swap. What does that make you think of? Inverse functions? Yeah, definitely related. And the symmetry that gave us that was like a reflection over the line y equals x. So we can describe this in terms of symmetry as well, in terms of symmetries as well. Reflect over y equals x. Here's the last one. Pi over 2 plus theta. And because the ideas that we'll use for this are relevant in the homework, let's do this not by trying to draw a picture. We could do it by drawing a picture. Instead, I'm going to say I can do this next one using entirely just algebra and previous identities. So keep these identities in mind. And let's try to compute a trig function at pi over 2 plus theta. And here's the logic I'll use. I know what pi over 2 minus would do. And addition is subtraction, right? Adding theta is the same as subtracting minus theta. Cool. Let's write down the relevant thing here then. What is the cosine of pi over 2 minus something? Flip back to the table if you need to. Cosine of pi over 2 minus thing is sine of that thing. So I'm just going to put that down because we are about to use that. So this is the thing that's going to be in the box. So the cosine of pi over 2 minus theta is the same as the sine of minus theta. Oh, cool. What's the sine of negative theta?
No, sine.
So look back to the formula, this table of formulas. And this one's also on the chalkboard. Sine of negative theta is the same as negative the sine of theta. So let's use this identity next. So, sine of negative theta is the same as negative sine theta. So cosine of pi over 2 plus theta, same as the negative of the sine of theta. It just took us 2 steps to get there. Let's play the same game with the opposite. So let's compute the sine of pi over 2 plus theta. We'll think of it as the sine of pi over 2 minus theta. And let's follow the exact same steps as above, just like with sine instead of cosine. So what can I do with that sine of pi over 2 minus? Open up to that Carvel formula page if you need to.
Which would be cosine of minus theta. Cosine minus or negative cosine of theta.
Let's do it one step at a time. So it'll be cosine of the thing in pink.
Yeah.
People agree? By this fact, pi over 2 minus, this fact. Cosine of pi over 2 minus a thing is sine of thing. Sine of pi over 2 minus a thing, oh I said the wrong one. Cosine of thing. So I just tried to deal with one ingredient of this at a time. And let's try to finish this up then. What's the cosine of negative theta?
Negative cosine.
Careful.
Is it that? Oh, just cosine.
Just cosine of theta. Right, that's the formula that we had on that cover sheet.
Yeah.
Oh, neat. So without having to draw any pictures, just by doing algebra, we extract the following. Sine of pi over 2 plus theta sine of pi over 2 plus theta is the same as cosine of theta. Cosine of pi over 2 plus theta is the same as minus sine theta. And all right, we did get all those things by looking at graphs. So the algebra agrees with that. We feeling pretty good? Let's use these to accomplish something. So here is essentially the homework posted for today. Let's suppose I tell you the following. I'm giving you an angle, alpha, which is in the first quadrant, and satisfies that cosine of alpha is equal to 3 over 5. Oh, Jesus. Do better. Okay, now it's going to stay focused. Good. All right. Let's try to figure this out. So I've given you an angle alpha. I'm telling you it's cosine and that it's in quadrant 1. Let's start with one thing. Is that enough information to figure out sine of alpha? Cool. Why? Or how, maybe?
Isn't it something with being added up to 1? Something with that.
Some things add up to 1. So what's the important fact about sine and cosine that involves adding up to 1?
That cosine squared plus sine squared equals 1.
The Pythagorean identity. So here's a fact. Sine squared alpha plus cosine squared alpha is equal to 1. You know cosine of alpha. You would like to know sine of alpha. That look like you could solve that for sine of alpha?
Can't you just draw a triangle?
Alternately, you can draw a triangle. It's in quadrant 1, so triangles make sense as a picture to draw.
Right.
So here's strategy 2. Oh, that's a really bad one. Or, all right, so there's a right triangle, there's an alpha. What sides of that triangle could I label?
Adjacent is 3, and then the hypotenuse is 5.
Cosine is adjacent over hypotenuse. Could you use that triangle to determine sine of alpha?
And then you just plug in the 3 to cosine squared
Yeah, so let's do it. If we do it this way, right, you would want to know, well, what is that? You would say, well, you need to solve 3 squared plus y squared equals 5 squared. That look like an equation that's easy to solve?
Yeah.
If you wanted to use this one, you would say, well, s is the thing I want to know, s squared plus 3/5 squared equals 1. That look like an easy equation to solve? Cool. Pick one of them, do it. Either way, tell me what you get for sine.
Four, 5.
I hear a 4 over 5. Do I hear a second for 4 over 5? Cool. How many people just did the pure algebra strategy? Cool. Triangles? Nice. The only danger in the triangles is the triangle might lie to you if you're not in the first quadrant, so you just have to think about that. But this one can lie to you too if you're not careful with the plus or minus sign that'll show up. And now, the rest of these entries are mostly easy. Do we have a formula that tells us what sine of pi minus alpha is? I'm just jumping down to item 7 because I don't want to do all of them. Yeah. By flipping back to that formula page, what is the sine of pi minus alpha?
Negative sine of alpha. Yes, sir.
It's just sine of alpha. And this is why it's worth like redrawing the picture. Pi minus alpha is go this way and then back by alpha. Those two differ by reflecting over the y-axis, so sine should stay the same. Oh, do I already know what the sine of alpha is? What is it? I didn't write it down. Think you could do that same trick for all of the items in this list? Most of them. Maybe these ones get complicated because I don't see any 3 pi over 2's in that table. But in order to complete this, let's use the same idea as we did to get the pi over 2 plus alphas. Start with this. Instead of thinking about 3 pi over 2 minus alpha, that's the same thing as pi plus pi over 2 then minus alpha, right? Is that true? Right, those parentheses don't actually matter. But they're helpful parentheses. Because what happens to cosine when you stick an extra plus pi? What does this do to cosine? Makes it negative. And still cosine? Nice. So this will be still, makes it negative, still cosine. Negative, so the pi on the inside is translating to a negative. Cosine of, and then the thing that I boxed in pink, pi over 2 minus alpha. Oh, do I know what cosine of pi over 2 minus alpha is? Yeah, maybe you have to look back at that formula table again.
Just sine. Oh, negative.
Cosine of pi over 2 minus alpha. So the cosine and sine just swap when you do pi over 2 minus a thing? So I had cosine, so we'll look at cosine. Pi over 2 minus theta just becomes sine theta? That's what y'all were saying? Awesome. So this negative sign will come along for the ride. That will now become sine of alpha. Oh, do I already know what sine of alpha is? What's the sine of alpha? 4/5. So I'm going to let this negative that showed up come along for the ride. Negative 4/5. Think something similar could do for the next 3 items? I bet. So, think in terms of this language on this particular homework. And see what you get. That seem all right? Cool. So I'm going to shift gears rather drastically. We are going to start up a new unit. Let's talk about inverse trigonometry. So, oh yeah, anyone else still need a copy of the notes? So let's think about like what I should mean by inverse trigonometry. So the trigonometric functions take an angle and give you like a y value of its sine. Inverse trig asks the opposite question. What if I tell you a y value on the unit circle and then ask you what angle gives you that? That's the job of the inverse trig functions. You can also think of them in terms of right triangles because trigonometry also says something about right triangles. So let's think in terms of right triangles. So, well, maybe a bit of motivation. There's the job of an inverse trig function. Suppose I want you to solve sine of x equals 1. And maybe it's a bit of motivation. let's think about that. What if I asked you to solve e to the x equals 1 over 8? What is the solution? What undoes exponentials?
Maybe x equals log e, and then 1 over 8.
Yeah.
Well,
Perfect.
sorry, natural log.
Yeah, but that's the same as log base e. Right? There's nothing wrong with saying log base e. It's just ln is shorter and it's a useful convention to have. So the job of logs was to undo exponentials. We want something that does that same job for trig functions. And let's think of it this way. So if I want you to solve sine of x equals 1/8, well, here's a picture of such an angle. Here's an angle whose sine is 1 over 8. Right? Just so katoa. So you can draw a picture of inverse trig functions immediately. And let's maybe describe it more. So this is an angle. It's an angle in quadrant 1, because visually, yeah, that angle's in quadrant 1, with sine equals 1 over 8. We'll make up some names for that angle. One of them will be sine inverse of 1 over 8. Right, just how when we talk about inverse functions, we put a little -1 in the superscript of the f. It's also an important enough function to have other names. One name for it is the arc sine of 1 over 8. And depending on what calculator you have, you may have a button that says a sine of 1 over 8 to compute inverse trig functions. So those are the functions we'll be interested in studying. Maybe I'll even invite people if they have their calculator on them. Take a look at it. You see something that says arc sine, sine inverse, a sine, somewhere on that front panel. Use it. Tell me, what is the inverse sine of 1 over 8 approximately? I hear a 7.18. Do I hear a different answer? Well, I should, because it's going to depend if your calculator is in radian or degree mode. And maybe even just by looking at that, does that look like an answer in radians or degrees? Degrees, right? 7 degrees would be reasonable for a pretty small angle, which this should be. It would be a gigantic angle in radians. It wouldn't even be in quadrant 1, would it? It would, but it'd be like all the way around the circle. What is it in radian mode?
0.25.
0.125 radians. Cool. So informally, when you think of these inverse trig functions, you should think of the simplest angle with sine equal to 1 over 8. And that word simplest is doing a lot of work. Because, right, apparently 7.18 degrees will have this value for sine. But what about 367.18 degrees? Will that also result in the same value for sine? Maybe compute sine of that better be about 1/8. So tell me, what is the sine of 7.18?
About the same as 0.125. Like 0.1249.
Yeah, but that's like rounded off, right? How about that? What's that about?
Zero
0.125, the same. And notice it has to be, I just added an extra 360 degrees. Adding 360 degrees won't change trig functions. So, this is the simplest is doing a lot of walking. Both of those angles are valid answers to what angle has sine equal to 1/8. That one's simple. Similarly, what do you think cosine of, let's make it negative, cosine of -1/8, what would you want that to mean? Based on the sentence above.
That's the best angle with cosine or cosine equals negative, cosine negative one negative one.
Cool. And maybe you could even like draw a picture of it. So let's see, it'll wind up being negative, so it can't be in quadrant 1, but I think there are simple angles in quadrant 2. And cosine is -1/8, so it'll be about there. That looks like it has cosine of -1/8. Cool. All right, so let's think in terms of like honest-to-God inverse functions. So there's the graph of sine and cosine. Which one's which? Which one's sine, which one's cosine?
Sine is the one that passes through the origin, so sine would be the one.
So sine, cosine. That's not important right now, but it'll be relevant in a second. Looking at those two functions, are they one-to-one? Do they pass the horizontal line test? No. So that's like kind of bad, right? Because what was special about functions that pass the horizontal line test?
They give you inverse, right? Or they had inverses.
Yes. So do either of these things actually have honest-to-God inverse functions? No. So that's like upsetting, right? I want to talk about inverse functions to these trig functions, but I've just said I can't. These don't have inverse functions. So that's like problematic. But it's not like a problem we haven't encountered in the past. And let's just see this. Y equals x squared, is that a one-to-one function? Does it pass the horizontal line test? No. Let's recall the horizontal line test. A function passes the horizontal line test if it intersects every horizontal line in at most one point. So, draw a horizontal line on cosine, just because that one looks less messy. How many times does that horizontal line intersect cosine? At least 4 times. If I continued the graph on, I think I'd get infinity times. So it fails the horizontal line test like really badly. It's not a one-to-one function, it's like an infinity-to-one function. Y equals x squared, does that pass the horizontal line test? Nope, there's a horizontal line which it intersects in 2 points. But if I ask you, what is the inverse to x squared, what do you tell me? How do you undo squares? Square roots. So, why is that? Well, the way that you get the square root function is you say, well, what if I only take that half of the squaring function, the bit that I just outlined in black, is that one-to-one?
Yeah.
Nice. Take the inverse function of that. And then you have to deal with the fact that you restricted domain, and this is why whenever you undo a square with a square root, you get a plus or minus sign. There'll be something even worse here. This isn't actually one-to-one, it's like infinity-to-one. So you'll lose kind of infinitely much information whenever you take the fake inverse that we'll invent. So, let's do exactly that. So here's what we'll do. Let's try to figure out how much of these graphs we can use while still having them be one-to-one. So let's start with sine. Let's start at 0 because 0 is a nice thing to include. How far to the right can you go while still having the function be 1 to 1? Either give me like the exact x value or like
It's like 1.5.
like 1.5-ish.
Yeah.
Because that's where that turning point is.
Yeah.
So let's fill that in, and then let's see if anyone remembers. Where's that turning point of sine? It is 1.5-ish. So sine starts at 0. It starts increasing. It starts increasing. It starts increasing. Once it makes it up there, it turns around and starts decreasing again. Pi over 2, which is about 1.5. How far to the left can you go while still having it be 1 to 1? I don't think you can get to negative 4.5-ish. That would be like all the way up here, right? 1, 2, 3, 4.
Oh, negative.
Right, like it's gonna fail being 1 to 1, like right there.
It'd be like, yeah, 1.5-ish too, so about 5.
Yeah, I think about there.
Yeah.
At that turning point, right? So I can use this much of the graph of sine. If I only saw that much of the graph of sine, would you say that that is a 1 to 1 function?
Yeah.
Awesome. There's something we can involve. Let's play the same game for cosine. Let's start at 0, x equals 0. How far to the right can you go while still having it be 1 to 1? About 3. Cool. So yeah, I agree, about 3, because I should be able to use like this much of the graph. What is the rightmost endpoint of that? It is about 30, but what is it exactly? So let's think about what cosine does. So cosine is the x value. It starts at 1. It starts decreasing, it starts decreasing, it starts decreasing. It makes it to negative 1 at what angle? 180 degrees. Well, pi radians. I like radians though. And then it starts increasing again. So I can't go past pi radians. It'll fail to be 1 to 1. That turning point is at pi. Cool. There's how much of the graph of cosine I can use and still have the thing be 1 to 1. So what's going to happen on the next page is I'm going to copy down exactly that much of sine and cosine. Then we'll say these are functions I can involve. We will involve those functions. Let's do it. And let's just check for typos. I guess this looks like it's the graph of sine of x. There's the graph of cosine of x. Do those agree with what we did on the previous page? Right down to the labeled endpoints? Awesome. So here's what I'll do. If you only saw those two graphs, are each of those graphs of 1 to 1 functions? Nice. They both now pass the horizontal line test. So I can take the inverse function and have something that passes the bottom line test. So, are sine and cosine 1 to 1 on these domains? Yes. Do they have inverse functions? Yes. And let's start by seeing how we've restricted the domain and range. So if you only saw that much of sine of x, what would you say the domain of this thing is? Negative pi over 2 to pi over 2? Including endpoints. I agree. And maybe I'll even ask the follow-up. Why? Like, how did you get that?
Because the domain's always the x value.
Yeah, perfect. Yeah. The domain is the x values you see on the graph. What about the range?
It'd be negative 1 to 1.
Negative 1 to 1.
That's the y value included.
Because it's the y values. And notice we didn't lose the range. That's the same as the range of all of the graph of sine. So we lost some domain, but at least we didn't lose any range. How about when we do this restriction for cosine?
Zero.
0 to pi? And what about its range?
One to -1.
Awesome. And conventionally, when you're talking about intervals, you put the lesser endpoint first, even though it looks like they've like switched order. That's just the notation in intervals. All right. So I want to invert those functions. So now I'm going to write down the super formal definition of inverse trigonometry. Inverse sine, also called the arc sine, is the inverse to the function sine of x after you restrict the domain to negative pi over 2, comma pi over 2. And let's think about what that means in another way. So inverse sine of y is an angle whose sine is y. And it is an angle that sits in this domain. So it is the angle in between negative pi over 2 and pi over 2, which satisfies that sine is equal to y. Feel okay right now? So whenever you talk about inverse trigonometry, you want to draw on the angle that's in between negative pi over 2 and pi over 2 and has that sine value. And same thing for cosine. Inverse cosine is the inverse to cosine after you restrict the domain to be 0, comma pi. So it is the angle between 0 and pi with cosine equal, well, you know what? Cosine is an x value. So I'm going to put an x in there. Right, there's nothing special about what you call that variable, but cosine recovers the x value. Nice. So, with that done, let's keep on thinking in the abstract. So let's compute some domains and ranges using this. So based on the stuff above this line on the sheet of paper, what would you say the domain of inverse sine is?
-1 to 1.
-1 to 1. Do I hear a second for that? I agree. I think that's right. How'd you get it?
Just with the x and y values.
Nice. Whenever you take the inverse function, you swap the x and y values. So this domain should be that range. Domain and range swap when you take the inverse function. So the domain of inverse sine is -1 to 1. Let's make that negative a little bit more convincing. What would you say the range of inverse sine is? Nice. Negative pi over 2 to pi over 2. And that again comes from like looking at that graph. Domains and range swap. You can also read it from this sentence. Inverse sine is the angle, so inverse sine is the output. The output is between negative pi over 2 and pi over 2, so that gives you the inputs of the range. Let's play the same game for cosine. What's the domain of inverse cosine? Same. The range? Awesome. And let's see if that checks out by, let's actually just literally graph. When you take the graph of the inverse function, you swap the x values and y values. So if there's the graph of y equals sine of x, then I want the graph of y equals sine inverse x. Negative pi over 2 comma negative 1 will become -1 comma negative pi over 2. Pi over 2 comma 1 will become 1 comma pi over 2. 0, 0 will go to 0, 0. This is like horizontal tangent, so there will be a vertical tangent there. There's the graph of inverse sine. Feel good? And let's see if that agrees. Is the domain of that function -1 to 1? Is the range negative pi over 2 to pi over 2? Awesome. And you can do the same thing for inverse cosine. Pi over 2 comma 0 will become 0 pi over 2. All right. Feel pretty good? All right. So here's the next couple exercises I want to do. It may look an awful lot like I'm not going to get through this section of the notes. That's okay, that's built into the plan. There were some updates I made to Canvas like last night that maybe you noticed. Night before? I don't know, doesn't matter. Let's figure out how to evaluate inverse trig functions using the unit circle. So, let's try to compute inverse sine of 1/2. So here's the way I'll do it. Grab your unit circle. Look for an angle in between negative pi over 2 and pi over 2, which satisfies sine equals 1/2. Do you see an angle that does that? What angle do you see?
5 or 6 or 30 degrees.
Pi over 6 or 30 degrees. All right, there's an angle. I see a 1/2 for the sine. It is in between negative pi over 2 to pi over 2. Sine is 1/2. So inverse sine of 1/2 is pi over 6. Feel pretty good? All right, and hopefully not so painful. So everything that you know about sine and cosine, you also know a corresponding fact about the inverse trig functions. This next one is more difficult, only because there's a negative sign. So let's compute inverse cosine of the square root of negative the square root of 3 over 2. So pull out your unit circle. Give me an angle which is in between 0 and pi, which satisfies that cosine is negative the square root of 3 over 2.
5 pi over 6.
Like you're 5 pi over 6? People agree? All right. And I know on the previous one, like I didn't even bother writing down the thing in degrees, but I think I probably should have. So inverse cosine of pi over 2, 1 over 2 is pi over 6 or 30 degrees, if you prefer. Inverse cosine of negative root 3 over 2, I'm a bad listener. What did you just tell me that it is in radians?
5 pi over 6.
5 pi over 6. And what is it in degrees?
150 degrees.
Neato. So, you can use the unit circle you have to make some computations automatically. Your unit circle is also a lookup table for inverse trig function values. It's just limited by the fact that we don't have that many dots whose addresses we know. We will get more eventually. Let's go back to thinking about right triangle trigonometry. There's a right triangle. Let's use inverse trigonometry to determine what alpha and beta are. So, let's look at that triangle. I'd like to know alpha and beta. What's something you can tell me about that triangle?
Is that 3, 4, 5?
3, 4, 5 triangle. So I guess you're telling me the missing side leg.
Yeah.
Cool. What's the missing side leg?
3.
3. So on the one hand, yeah, you can totally know that as soon as like 3 squared plus 4 squared is equal to 5 squared is something that you should just like have in your head at all times. So if you see a triangle that has a 3 on an edge and a 5 on the hypotenuse, you know the other before. All right. Is that everything I want to know about this triangle then? What else could you say using this triangle?
The inverse to find alpha.
Let's use an inverse trig function to find alpha. So to do that, let's write down an inverse trig function of alpha. So give me a trig function, not inverse, just a trig function. I don't even care which one.
Tan.
Tangent. Yeah, sure. No, we haven't talked about inverse tangents. Nah, I lied. Using this triangle, what's the sine of alpha?
3/5.
Ooh. Alpha is an angle that is in between negative pi over 2 and pi over 2. In fact, it's between 0 and pi over 2. And its sine is 3/5. This alpha is an inverse trig function angle. So I can just write down what that angle is. It's the inverse sine of 3/5. And if I now want a decimal approximation, I know how to get one, at least if I'm allowed to use a calculator. Calculator is going to do something fancy like it use a Taylor series. What is the inverse sine of 3/5? And make sure you say whether you're on degrees or radians in your answer.
In degrees, it's 36.86 degrees.
36.86, I'll round that to 36.9 degrees. People agree? Anyone get the same thing but in radians instead?
161.
Nice. Is there another trig function that we know what alpha is under? In fact, any of them, right? In fact, let's go back to tangent, just for laughs. What's the tangent of alpha? 3/4. We haven't talked about inverse trig functions, but this is an angle in quadrant 1, so probably nothing goes wrong. I bet this should mean that alpha is tangent inverse of 3/4. And let's just check if it is. What is the inverse tangent of 3/4? Oh, I'm running low on time. I'm basically out of time.
0.64.
Are you at 0.64? That's in radians, I guess.
Yes.
All right. So as soon as you have a right triangle, you can determine all of the angles inside of this triangle by using inverse trigonometry. By just taking the appropriate inverse trig function. So that is where I'll stop for now. Let me give you a tour of what's left in this section of the notes. There will be another example super similar. So maybe try to figure out alpha and beta for this next one. Our next thing to think about is what happens when you compose trig functions with inverse trig functions. They really want to undo each other. But just how like square roots and squares don't quite undo each other, there will be some weird issue with inverse trig functions undoing each other. And that's what we'll finish up on next time. We'll talk about how to actually compute inverse trig function of a trig function.